Gradient descent method is first order optimization method. And when we can compute the second order, the Hessian, and when we can utilize the Hessian matrix as well, we can speed up the conversion speed. So Newton's method is one kind of second order optimization approach. So basically the most famous second order method is Newton-Raphson's method. So here the goal is find the zero of differential function, gradient of f is equal to 0, so the critical point. So the method xt plus 1 is equal to xt minus x over f prime xt. So when we iteratively compute this one, then we can find the best solution very quickly. So what was the idea? So here, let's say this is x-axis and this is y-axis. So xt plus 1 is equal to xt minus fxt over f prime xt means you draw the first derivative value. So let's say this is xt, draw the first derivative value and find and this one as xt plus 1. Okay, so this is Newton-Raphson's method. Why this is second order method? So here this approach try to find the not gradient, but fx is equal to 0. Okay. The Newton-Raphson's method is an efficient method to find this fixed point fx equal to 0. So when we replace f to f prime to f2 prime, second derivative, then this Newton-Raphson method can find f prime is equal to 0. Okay. So the Babylonian method is this. Let's say fx is equal to x squared minus r, then Newton-Raphson method, find xt plus 1 in this way. And then the conversion speed is this. Assume the x0 minus square root r less than or equal to 0.25 and r is 1 over 4. Then xt plus 1 minus square root r is equal to 1 over 2 times xt plus r over xt minus square root r. So this is equal to 1 over 2 xt times xt minus square root r square. And since we assume that this r is greater than or equal to 1 over 4 and xt is greater than or equal to 1 over 2 because of this condition, and and this condition as well. So xt plus x capital T minus square root r is less than or equal to xt minus 1 minus square root r norm square less than or equal to xt minus 1 minus square root r square of square. So we can make inequality iteratively. Then in the end, we finally have x capital T minus square root r less than or equal to 2 minus 2t. So here square root r is the critical point, is the global optimal point. And from this analysis, we can bound the distance between the x capital T, our observed point after capital T number of iteration with Newton-Raphson method. So the error is bounded by 2 to the minus 2 capital T. So this is double exponentially fastly converts to the critical point. This is very, very fast, right? So here I didn't explain why this inequality hold, because xt is always greater than or equal to 1/2. So this value is always less than 1. So we can basically say xt plus 1 minus qt r is less than or equal to xt minus qt r square. So from this result, we have these inequalities. So Newton's method can find critical point when you replace f to f prime and f prime to f2 prime. So we have this one. Xt plus 1 is equal to xt minus f prime x over f2 prime x. For d-dimensional case, instead of just f2 prime x, we have to use Hessian matrix because Hessian is the second order gradient. And we have to use inverse matrix because Hessian is a matrix. So this is the Newton's method. We update xt plus 1 from xt minus the Hessian inverse matrix times gradient of fxt. So let's compare gradient descent and Newton's method. So here in the gradient descent method, we just simply having xt plus 1 equal to xt minus gamma times gradient of fxt. And so we just multiply the step size gamma to our gradient. And this is equal to gamma times identity matrix times the gradient vector. But in Newton's method, instead of just simple gamma times identity matrix, we use Hessian matrix. So the Hessian matrix is just replace the step size times identity matrix by the inverse of Hessian matrix in Newton's method. And one nice thing of inverse Hessian matrix is inverse of Hessian matrix is can describe the Hessian matrix having the information on the local surface of your loss function, so the curvatures and everything. And the inverse Hessian matrix actually make your local area very regularized, so that your gradient descent step does not make a very zigzag behavior or very slow convergence behavior due to the very high beta over alpha thing. So when we study the convergence speed of gradient descent algorithm, when the function is alpha strongly convex and beta smooth, then the value beta over alpha was very important. And when beta over alpha is very, very high, extremely high, then it was very difficult to find a fast convergence result because the contour of your loss function looks like this, and then there is some zigzag behavior, or if we use very tiny step size, then we can escape from the zigzag behavior, but the convergence is very, very slow because our update is too tiny, right? But with Newton's method, the inverse Hessian make your loss function surface looks like this. This change your space more regular. So your gradient descent more directly compared to the global optimal point, and then you can reach to the global optimal point with a few steps. Right. But anyway, when Hessian matrix is equal to some beta times identity matrix, then Newton's method is equal to this. For instance, if your function f is just a second order polynomial function then this holds.